If you would recall, last week we started talking about double integrals. We went over the thinking about what a double integral represents and how we think about the calculation and how the notation comes together. When we see a double integral over a region of some function f of xy times dA, the thinking is the same. We're going to evaluate this expression f of xy times dA at all the points that are listed in the double integral part. The integral part is telling us what to plug into that expression. It's where we're going to evaluate f of xy dA. And then we're going to add up the results. This is just the continuous version of breaking an area into rectangles and calculating the area with length times width. We've just upped this to the volume under a surface. So we're thinking of f at xy as the height of the surface over a small piece of the rectangle, the region R, this little rectangle dA. So what we're looking at here is height times area to calculate volume. The thinking is the same as it was before with definite integrals calculating area. We're going to flatten out our continuously variable functions so we get to use multiplication. And then we're just going to do that more and more often and use our discrete sum to approximate our continuous sum. That's just how sums work. And then we get the big revelation that we can do this with antiderivatives. That's like the big deal in calculus. That's the big finish. We get to use antiderivatives to calculate this area, to add up this continuous sum. So our job in double integrals is not so much to think about how this is set up, because the setup is the same. Our new job, the new challenge with double integrals, is describing the region in a way that the integral will understand. So our new job Our new task for double integrals, since we understand how they're constructed, is to describe the region over which we are integrating. Our new task for dealing with double integrals is to describe the region R. The first way that we get to go about this is just take what we did before in an integral of a single variable function and say, what's x between? And just add to that. So to describe the region, we're just going to say, what's x between? What's y between? We're going to describe the region in intervals. We're going to say, what's x between? And then we're going to say, what's y between? Or we're going to do this in the other order if that's convenient for us. We might start by saying what's y between, then finish by saying what's x between. So once again, to practice this task, we're going to be looking at our integrals from the top down. We're not going to worry about what's going on with the function We're not worried about what's going on with the function. The function has to be something that's given to us or something that we have to figure out. That's just the height of the ceiling. Our job right now is to learn how to describe the floor. We're describing the set that we're trying to plug in to the function times dA. Right now, our job is to just describe the floor, not worry about describing the height above it. Because when it comes to calculating the height above it, it's just antiderivatives, and y'all already know how to do that. I know it's like functions of two variables, but I promise you, y'all already know how to do that. I could give you a quiz on that right now, make you guess at how it works, and you would be fine. Because it works the same. What we're going to do is practice describing the floor, and we want to set it up in two different ways. We want to set it up with what's x between, then what's y between, and also the other way around. What's y between and what's x between. So we're going to set up two different double integrals. We can set up an integral in the order dx dy, where we first describe what x is between with this first integral, and then we describe what y is between in the second integral. Or we can write the double integral in the other direction. Other direction, other order. Start with the inner one being what's y between, and the outer one being what's x between. There were some rules that we had for what we can describe when we say what's x between, what's y between. The last integral has to use constants. So whatever else goes on in describing our region, the last integral has to use constants. So by the last integral, I might also say outer integral. We have to finish with just constants. The last integral only gets constants. The early integrals can use functions of upcoming variables. Early integrals can use functions of upcoming variables. So this integral, the y integral here, and the x integral there. I don't want to phrase this as first and second because that stops at 2. I definitely want to have one that's called the last one or the outer one. That one is constants. Any ones that come before that, because we're going to stack more integrals inside here as we go. So in describing what's x between or what's y between, early on, we can use functions of any variables that are coming up. But when we get to the end, when we get to that last integral, we only get to use constants. Now, in the case of this rectangle here, x is between two constants always, and y is between two constants always. X goes from 0 to 9. I can use that inside or outside as not variable. And y goes from 0 to 3. That's also just an interval because we're looking at a rectangle. A rectangle is just two intervals. Life is easy with rectangles. What we're going to do now is continue what we were working on last week, where we start dividing this region up by cutting through it with some functions. And we say what's x between and what's y between. Now we're going to we're going to write two double integrals to describe the region. So I'm going to throw in I'm going to draw a line. I can't remember what line I used last time. Let's draw a line from 0, 3, drop it down to 9, 0. And our region is down here. So the region is that lower triangle, bounded by the x-axis, the y-axis, and that line. Let's describe that line since it might come up. That line is y equals 3 minus, looks like we lose 1/3 for x. We drop by 3, change in y is 3, change in x is 9. So our line here, y equals 3 minus 1/3 x. Not the only way to describe that line, but since we have the y-intercept sitting right there, let's use the slope-intercept form. Now I want to set up two different integrals. I'm going to set up a dx dy interval. And a dy dx interval. The easiest place to start is the last place that we would actually calculate. It's easiest to start with the last integral because the last integral has to be constants. So if we look at what's x between, whatever else is going on with the region, the smallest x is 0 and the largest x is 9. And the same thing happens in y. It's just between 0 and, well, not the same thing. They're different values. Look for the smallest x, the smallest y, then the smallest x, the largest x, the smallest y, and the largest y. The constant interval is always easiest. That's all. The easiest, what's this between? So then we need to describe where we're starting with each of these. So in the dx dy double integral, the outer integral is a y. Y goes from 0 to 3. The last integral only gets to use constants. So all the y's go from 0 to 3. Now what we're going to do is pick a particular y value and say, what's x between? So for a particular y value, what's x between? So the region, x starts at 0 and ends at the line. For a particular y value, x starts at 0 and ends at the line. So x starts at 0 and ends at the line. Notice that I can't write I can't write 3 minus 1/3 x there, because that's not what we're saying. We're saying x equals 3 minus 1/3 what x is what y equals. So I got to rewrite this. I'm going to subtract 3 and give myself enough space. And then I'll multiply by -3. So x will go from 0 to the line, which described in terms of x is 9 minus 3y. And y goes from 0 to 3. The last integral has to be constants. In the dy dx integral, things will look different. The last integral is the x integral. And so that's the one that has to be constant. So x goes from 0 to 9. The last integral, we only get to use constants. For the y integral, we're going to look at the region. We're going to pick a random x value in the region and say, what is y between? For this random x value, y starts off at 0 and ends at the line. Here we can use the description for the line 3 minus 1/3 x, because that's a y equals description of the line. So the line we can just replace with 3 minus 1/3 x. Any questions? Just what's x between? What's y between? Last integral has to be constants. Let's take the same region. Here's, let's say, R1. Let's take the same rectangle and divide it up and instead try to look at R2, the region above. So this is for R1. I'll call that the lower triangle. Let's say that R2 is the upper triangle. So R1 is this one down here. And then R2 is going to be the one up here. We can describe it in two different ways. An integral with a dx dy, and an integral with a dy dx. Double integrals, always a 2-for-1 deal. You need to be able to like copy and paste like the handwritten stuff. I know I could do that with technology, but I'm like writing things by hand, so. Future, I guess. All right, let's set up these two double integrals. Now, the best place to start is the easiest place. So we're going to look at the last integral that only gets constants. So in our dx dy integral, y has to be constants. Y goes from 0 to 3. Now, when we describe, if we pick a typical value of y, now we're going to be looking at a different starting and ending place for the x. Now we're saying, what does x go between? But this is in R2, that upper triangle. So, right, if I pick this y value, I don't actually hit R2 until I get to the line. So it's at the line. That's when the region starts, and the region ends when x gets to 9. So for a typical y value, we start at the line and end at 9. In the dy dx integral, the dx is the last integral, so we have to use constants. X goes from 0 to 9. We only get to use constants on the last integral. For dy, the same thing happens. We start off at the line and end at 3. So we pick a typical x value, and we start drawing a line when we hit the region. We start at the line and end at 3. So y goes from the line up to 3. These two double integrals describe the same region, that upper triangle. Question? Simple, right? What's x between? What's y between? Just follow a couple of rules. Draw a picture and just look. Where do we start? Where do we finish? We're going to do the same region, but we're going to split it up slightly differently. Same rectangle, not the same region. I have a rectangle that's 9 on the x and 3 on the y. So you could probably guess how I'm going to be splitting this region up. The only question is where I'm going to start at 0, 0, or I'm going to start at 0, 3. I'm going to start at 0, 0 because it'll make it like a little easier to draw. I'm just going to take this problem up 1 degree. Instead of splitting up this rectangle with a line, I'm going to split this rectangle up with a parabola. I went from a degree 1 dividing line to a degree 2 dividing line. This is because I'm known in the business as, I'm known as what's known in the business, hella predictable. Notice that we're still inside the same rectangle. It's just a matter of where things start, where things end. So this is still from x equals 0 to x equals 9, and y equals 0 to y equals 3. That part doesn't change. What changed is the dividing line. Instead of having a line going from 0, 3 to 9, 0, I've got a parabola going from 0, 0 to 9, 3. That parabola, we can either describe y as the square root of x, if I happen to be describing the parabola and I need y equals, I'm going to say y equals the square root of x. Or I can describe that parabola in terms of x by saying x equals y squared. This is the positive part of the parabola, x equals y squared. The negative part of the parabola would be down here below the x-axis. But that's not y between 0 and 3, so I'm not worried about that. Now we just have to figure out which region do I want, the top portion or the bottom portion. Let's make R1 this top portion. And we're going to do the same thing. We're going to make a double integral, f of x, y. The function is not relevant. We're still just describing the floor. It's going to be a dx, dy, and then we're going to make a dy, dx. Yeah, I need a stamp for this. Start with your last integral first when you're setting up your double integral, because it has to be constants, and the constants are easy to pull. So what's y between? As the last integral, y goes from 0 to 3. Then for a typical y value, I'm going to see where does x start and where does x end. So for a typical y value, x starts at 0 and ends at the parabola. X starts at 0 and ends at the parabola. What's x between? What's y between? Or what's y between? What's x between? In the dy dx integral, x is the last integral. So we just write down the constants, the lowest, the smallest and largest values of x. X goes from 0 to 9. Now we write down what's y between. So we pick a typical x value. Here's a typical x value. And we find the smallest y value in the region. And that starts at the parabola, and it's going to end at 3. So y will start at the parabola and end at 3. We changed our description of the parabola to the y equals version because that's what we're saying. We're saying what's y between? The parabola in terms of y and 3. Now let's describe the bottom part. This boundary, this parabola boundary has divided our region or our rectangle into two different regions, a top part and a bottom part. I almost said top half and bottom half, but they're not halves because they're not the same size. Because I didn't use a line. So the last integral is always easiest in the dx dy integral. Y goes from 0 to 3. We don't worry about any curvy parts. Y goes from 0 to 3. For the x, we're doing the opposite of what we did in the top part. Here, we're going to start at the parabola and end at 9. So now if I pick a typical y value, I start at the parabola and end at 9. In this case, the parabola in terms of x is y squared, and we stop at 9. Then for the dy dx integral, double integral for R2, the bottom part. Now x is the constant, so we just go from 0 to 9. Then we pick a typical value of x and say, what's y between? So here's a typical value of x, and I'm going to draw a segment in R2 starting at 0, and y ends at the parabola. So here y starts at 0 and ends at the parabola. I have to describe the parabola with the y equals because we're saying what's y between. Questions? Comments? Snide remark? How's everybody okay? See, snide remarks are more difficult because even if I turn my back, there's only 4 of you in the room. So if you like say something, it's like I kind of easily figure out who said it. So I turn around, and someone's like, "Oh, snide remark." I'm like, "Oh, who said that?" I was like, "Oh, I know exactly who said it because I just have to like echolocate to like the position in the room, right?" You're all kind of sitting on a line here, so I'd have to go by distance. It's just these two guys in the middle. They're kind of almost equidistant from me, so that'd be the hardest one. So I don't know. You might have to put on a voice too. Also, if you make a snide remark on the chat, like your name is like right on it. You can't do anything anonymous on the chat unless you make a whole separate account just to log in, just to make snide remarks. But then you'd have to have both of them running, which you could do. So I guess that would totally work. You just log in from your computer, and then from your phone, you log in as well as anonymous guest. And then you're like, all snide remarks, which would be a weird thing to do because I specifically requested snide remarks. So it's not like you're going to get in trouble for it. You know what I mean? I might judge the quality of your snide remark though, because if it's just like all mean, then that's not cool. That's just like, it's boring. So if I like turn around and you're like, "Oh, fuck you," I'm like, "Oh, well, I'm not even gonna react to that." That's a snide remark that's so bad it's not even wrong. I mean, it's just like, eh. So remember what we're doing when we set up an integral. Not just a double integral or a single integral, but later on triple integrals, integrals with vector valued functions, which we haven't even mentioned until now. But this part of the integral with the swoopy s's, that's just telling you what to plug into the rest of it. Do this f of xy times dA for all these x and y values. Right now, life is pretty easy. We get to describe just what's x between and what's y between. When this eventually and inevitably gets upgraded further, say to a function of 3 variables, say with an x, a y, and a z times dv for volume, I guess, I'd have 3 integrals. We're going to do the same thing. What's x between, what's y between, what's z between. Same thing. All right, that's it for today. We're just thinking about what's x between, what's y between. You make a little rectangle. You divide the rectangle with up with some known function, and you get like 4 things that you can practice on. Dx dy for a one half, a top half, and a bottom half, or a left half and a right half. I don't know. That's your call. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Week 8, holy cow.